Okay, so let us get started. So this module is support vector machines. It's also a binary classification based approach like logistic regression. So typically we have a data set with features and two classes. In logistic regression, we used class 1 and class 0. Class 1 was the desired class, like the spam email data set. If you remember, the spam class was used designated as class 1, and the not spam was designated as class 0. So basically, the kind of approach we will or strategy we use is the targeted class or the desired class we want to identify in the data set, we will use it as class 1 in all the algorithms. So again, this is also a binary classification algorithm like the other algorithms we have seen so far. We use class 1 for the desired data set and class -1 for the other data set. So that's the strategy we follow here. And so in logistic regression, we consider all the data points to come up with a decision boundary, if you remember. Instead, in support vector machine, what we will use is we'll consider only the data points that are closer to each other across the two classes. So that's the most important point. So we'll consider only the data points that are closer to each other across the two classes. So for example, consider this data set where we have two features, x1, x2, and if you plot the raw data as it is, this is what we have. And we have class 1, which is the red class or the red data points here, and class -1, which are the green data points here. So instead of considering all these data points to build a model, we'll one second. We will consider only the data points that are closer to each other across the two classes. So basically, we consider these two green data points and this red data point. So these are the data points that are closer to each other across the two classes. Now, so we would like to choose at least two data points from each class, if possible. So from the red class here, we can choose only one data point as the closest data point to the other class. So that's fine. But in the green case, we could find two data points that are closer to the other class. So we'll have two data points at least from one of the two classes. And the margin of separation. So what we'll do is we will try to connect the data points. So first of all, the data points that we choose from each class are called the support vectors. Okay. So these three data points here are called the support vectors that are closer to each other across the two classes. So what we'll do is we'll try to connect the support vectors in each class through a line. So here we are dealing with two-dimensional system, and that's what we'll do for our examples here. Later, I'll introduce the terminologies. For now, we can use the line as a terminology. So basically, what we'll try to do is we will try to connect the support vectors in each class through a line. And the two lines in this case, because we have only two classes, we'll have only two lines. The two lines need to be parallel to each other. That's the most important thing. So you cannot just arbitrarily connect them. So the support vectors also need to be chosen in such a way that the support vectors in a class can be kept using a line that is parallel to the line connecting the support vectors in the other class. So for example, if you choose two support vectors, like we'll do some example later, like this using, okay. So if we choose, for example, here, so you want to choose these two, we could also choose this as a support vector, but we just go with these two because these two are more kind of closer to the other ones, even though this is kind of closer to this overall other class, will choose these two as the support vectors because these are distance-wise kind of closer to the other class, even though this is also in the boundary. Okay. Anyway, so the line that connects these two support vectors, if you have chosen this, it will be the third support vector as well, needs to be parallel to the line that connects the support vectors in the other class. Okay. So again, we could have chosen this one as well as a support vector, but as I said, once we have two support vectors that are closer to the other class, that's good enough. We if there's some data point like this that's also on the boundary of a class and close to the other class, we could include them as well. But including more support vertex does not do anything better than just two. And it's also important to have at least two support vectors from one of the two classes. The reason is this. So like we see here, we before I say that, explain that, we by kind of choosing the support vectors from each class and trying to draw parallel lines connecting them, we're trying to find what's called a wide margin decision boundary. So the decision boundary basically is going to be an equation that characterizes these lines that connect the support vectors. So it's going to be something like this. So we're going to find an equation for this line that connects the support vectors in the green class, and an equation for the line that connects the support vectors in the red class. And the region of separation between these two lines is called the decision boundary. And we would like that decision boundary to be as wide as possible. So it's called like we are going to target for a wide margin decision boundary. And we're going to find this equation for a line that will kind of divide this decision boundary equally. And so that's the kind of target that we're going to equation that we're going to find. And once we find this blue line, we can find the equation for the other two lines as well. So we would like the decision boundary to be as wide as possible. So that it really depends on the support vectors we choose. The margin of the decision boundary that we come up with really depends on the support vectors we choose. Okay. So for example, if if let's say the same data set over here, it will look little kind of more terminologies in the beginning, but once we get going, things will be clear. Things will be with examples. Just stay focused and everything will be clear. All right. So this is one support margin that I chose as chosen. Now we could so for example, let us see. Um, okay, let's do this. So we could connect we need a parallel line. So instead of using this as a support vector, we could use this as a support vector. And so we have at least two support vectors from one class, so that's good enough. So we could kind of go for this. So if you compare this with this, so we should go for the one on the top, this one as the as the margin, because if you go with the one that is that I'm showing here, the width of the margin is not as large as this one. This is a wide margin decision boundary. So we should go for this decision boundary over here. So this is, we'll target for the maximum margin decision boundary. So depending on which support vector we pick, that will decide the margin decision boundary. So the algorithm has no control on the margin of decision boundary. It's we, the user, who has to choose the appropriate support vectors. So that's kind of part of the data analytics process. It's first important, we have, especially for support vector machines, we have to visualize the data in the coordinate system. So if we don't visualize the data in the coordinate system, it's not easy to identify support vectors. Okay, so we need to appropriately identify the support vectors so that we are able to find a maximum margin decision boundary that separates the two classes. And accordingly, we need to choose the data points as the support vectors. Okay, and as I said, we need to have at least two support vectors from one of the two classes. Preferably, we could have two support vectors from each class, but at least two support vectors from one of the two classes is important. Okay, and I'll tell you the reason for that soon. Let's go back to this slide. So if we don't have, or or we can say like this. So if we have just one support vector from each class. So if you have only one support vector from each class, let's say like this, I include this green data point as a support vector and this red data point as a support vector. It really depends on the data, the numbers that are part of the support vectors, because you're going to go through a lot of math, a Gaussian elimination method to solve some simultaneous equations and all these things. So it really depends on the numbers that are part of those data points that will decide the direction of the decision boundary. So what I mean by the direction of the decision boundary is, if you go back to this slide, so if we choose, if you again look at this example, so by choose the direction is also decided. Okay, so this decision boundary is kind of in this direction, facing down like this, whereas this decision boundary is kind of more inclined like this. So we are able to set the margin of the decision boundary as well as the direction by choosing at least two support vectors from each class. Well, at least two support vectors from one of the two classes. Okay. So by choosing two support vectors from this class, you are able to draw a parallel line that connects them, and the line that goes to this support vector in the red class needs to be parallel to this. So that decides the direction of the decision boundary. Similarly, by choosing these two support vectors and joining them through a line, and we need to have a parallel line that goes through the red support vector. So that needs to be parallel to this. So that decides the direction of the decision boundary as well as the margin. So if you have only one support vector from each class, that's a problem. you don't have any control on the margin of the decision boundary as well as the direction. So you may choose these two support vectors, these two data points as your support vectors, and run through the algorithm, the math. It depends on the numbers that are part of the data points. The margin of the decision boundary could be this, and the direction could be this, or it could be as small as this, and the direction could be this. So you don't have any control on it. That's why, in order for the user to be able to decide or identify the maximum margin decision boundary, we need to have at least two support vectors from one of the two classes. Okay. And that way we can decide, we can have control on the margin as well as the direction of the decision boundary. Now, so far I said we need to have the support vectors to be the data points that are closer to the other class. Okay, so this support vector is kind of closer to this. This is also closer. The red one is also closer to this. And the previous example, these two support vectors are closer to the red class. Now, if you look at this visualization here, if I go strictly with the criteria that the data points that are chosen as support vectors need to be the ones that are closest to the other class, we could go with these two data points as support vectors with the red class. And since we need two data points, even though this is the closest, the green data point on the top is the closest, we need to include this. And that's why we need to, because we need two data points from one of the two classes. It's not possible to have two from the red class in this layout here, so it's better to go with the green one. So if we go with these two support vectors and connect them using a parallel line, you get this parallel line, and this is the decision margin. Okay, so margin of the decision boundary. On the other hand, if you can be a little flexible with the criteria of choosing only the closest data points to the other class, if we choose these two data points and connect them using a parallel line, we can have the other parallel line going through like this in the red class, and we can have a decision boundary that is much wider than the previous margin. So the idea is this: if you remove these two lines for a second, let me just do this. If you remove these, so now if you just look at this visualization over here on the left, it looks like the green data point here, this one, is more closer to the red data points compared to the other green data points here. Okay, so all the other green data points are kind of more closer to each other compared to this one. This one is more close to the red data points. So we could treat this green data point over here that is close to the red data points as more like an outlier in the green data, among the green data points. It's not really reflecting the characteristic of the green class over here. So that's the idea over here. We could treat the this green data point that's more closer to the other class rather than its own class as more like an outlier and not a reflection of its own class. So we could allow such outliers to be in the margin. So before I said we don't allow any, or not, it's not we don't allow, we would prefer not to have any data point within this margin of the decision boundary, because that's why we choose the data points that are more closer to the other class as the support vectors. So we will try to have any, we try to avoid basically We try to avoid any data point to fall within the decision boundary. So that's why we want to separate the two classes as wide as possible, such that we don't have anything going wrong with the prediction. So you want to be able to model the training data set in such a way that the two classes of data points are separated by as wide decision boundary as possible. And it is the user who chooses or who basically has control on the decision boundary that is identified. We need to visualize the data and choose the support vectors in such a way that we can form a maximum margin decision boundary. So, if you go for these two data points as support vectors in the green class, you're able to have a much larger margin for the decision boundary compared to this one. And that's fine to have in a support vector machine. And such a support vector machine that allows some outliers to be part of the decision boundary is called a soft margin support vector machine. Okay, so we would preferably try to go for a hard margin support vector machine. That's basically the kind of like this that don't have any data point within the decision boundary. But if by allowing one or few, there's no particular number, but so we'll just say few outliers to be part of the decision boundary, we can find a margin that is much wider, then we can go for that decision boundary. Then we will say we are going for a soft margin support vector machine rather than a hard margin support vector machine. And we can find both. Basically, you're going to run some math and find some equations that characterizes this decision boundary. So we can go with both and find the equations that characterize the soft margin and hard margin decision boundary for the same data set. And then we run through a lot of test cases and try to find out which support vector machine is more accurate in classifying the test cases. Okay, so that's something people typically do. If you're not sure of which one to go for, you go with either you do the math for each case and get the equations, and then when you do the testing with the test cases, you try to then evaluate the two support vector machines and go and choose that and finalize that support vector machine that gives you higher accuracy in the prediction for the test cases. So that's kind of an introduction about support vector machines and what they do. So let's slowly start to get into the methodology. So the first thing we'll do as part of the math process with the support vector machines is, given the raw data set, or I'll call this actual data set, we visualize them like this and identify the support vectors. So that's the first thing, basically. Visualize the raw data set and identify the support vectors such that the margin of the decision boundary is as maximum as possible. But in terms of the math, the first thing that we'll do in terms of the math process is to normalize the data. So if once we normalize the data and visualize the same normalized data, the layout of the data points will be the same as the layout we had at the visualization for the raw data set. So the same data points that we chose as support vectors to the raw data set will end up being, or will look like to be, candidates for support as support vectors in the normalized data set as well. So normalization will not change the support vectors, so which data points you find as candidates for support vectors. They're going to be the same. Okay, so the reason why we do the normalization is the raw data, the features in the raw data may be of different scales. One feature may be just from 0 to 1 or 1 to 2, whereas the other feature may be sorry. Whereas the other feature may be like from 10,000 to 20,000 or so on. So that's why we normalize the data set. So we kind of transform, or we kind of instead of saying transform, move, we can say all the feature values in a comparable scale. Okay. And the way we'll normalize this using the mean and standard deviation of the features. And I'll show a lot of examples as we do start doing the examples. And one other thing we'll also need to remember is, so if x1 equals, sorry, if x equals x1, x2, so x1 and x2 are the two features, and we have a data point that has the values of these two features, and we say x equals x1, x2, or the actual coordinates of a data point in the original data set when you visualize it. We'll add a kind of one more kind of dimension, we can say. It's a dummy feature, basically, like we did in logistic regression. We add a dummy value of 1 to all the records. We do the same thing here. So in the normalized data set, we'll have normalized x1, normalized x2, followed by 1. And the 1 really kind of will count for the bias. And we'll talk about bias more as we proceed. It's more like the theta 0 that we had as a dummy feature, and to kind of account for that in logistic regression, we added a 1 to all the let me just open a slide for logistic regression. Added a 1 to all the records. Same thing here. So to account for this theta 0 in the feature vector, we added 1 to all the records, so that we are able to multiply, do the dot product of theta and x. So the same idea here, we add a 1 to all the records or the data points, and the feature vector here we'll call as a weight vector. So again, we're going to fit the data points and find the values of the parameters, theta 1 and theta 2, that together with the bias will form the weight vector. Okay, so this is for two-dimension data. We have two features. So given the two features, x1, x2, we are going to find a weight vector given by theta 1, theta 2, and a b. So the b is more like a theta 0 that we had in logistic regression. Only difference is we don't use theta 0. In logistic regression, we use theta 0 as the first parameter, and then theta 1 and theta 2, whereas here we put the b at the end and say it is theta 1, theta 2, and b. That's the only difference. And then, so accordingly, the 1 will be added to the end instead of at the beginning in the records for the data set. And we do a similar dot product of the two vectors, the weight vector. So instead of calling it as feature parameter vector there, we call this parameter vector and feature vector. So here it calls the weight vector and the feature vector. So we take a dot product of these two vectors, w and x, and the equation of the decision boundary or the line, basically, that separates the two or that kind of divides equally the decision margin. So this is like the green line and the red line, or the two lines that connect the support vectors. And we call that as the width of the decision boundary. So this together is called the width of the decision boundary. And basically, the Wx equal to 0 line kind of divides this margin equally. Okay. And so such that the equation of this line that connects the class 1 support vectors will be called Wx equals 1. And the equation of this line that connects the class -1 support vectors will be W times X equals -1. Okay. So the kind of, the the equations are going to be fixed. W times X equals 0 for the dividing line, and Wx equals 1 for the class 1 decision boundary, and Wx equals -1. So it depends on the two, basically the support vectors across the two classes that we have chosen, which will form these x, Wx equals 1 here, and Wx equals -1. So the support vectors are basically the x that will be part of this equation. So this equation will satisfy, or basically you can say this data point will satisfy Wx equals 1, and these two data points will satisfy Wx equals -1, because we are going to form the, or identify or determine, it's appropriate, the values of the parameters theta 1, theta 2, and b based on the support vectors we choose. So they are going to satisfy those equations. Okay. Now, this is something we could do later also, but I'm introducing right now here, and then we'll apply this approach when we go to the examples. So as part of the math, what we will do is we will find something like this. So given this normalized coordinate system, how to get the equation, how to basically plot this line, Wx equals 0. So again, this is your theta 1, theta 2, and b, and we can say W times x equals 0. So this 3.2212 times x1 plus 0.3504 times x2 minus this thing times 1. So this is minus 1.133. Basically, you're multiplying these two. So theta 1 x1 plus theta 2 x2 plus b times 1. So that's what we get here on the left side equals 0. So that's the equation of this line that divides the decision boundary. So how to plot this the coordinate system is, so we need to basically find two data points that through which this line goes through. So how to find those two data points through which the line goes through, so that we can connect those two data points, and that will give us the line in this coordinate system. So an easier approach is, if you set x1 equals 0 in this line, it's basically reduced to this. 0.3504 times x2 minus 1.1383 equals 0. And through the math, we can get x2 be 3.2486. So the line does go through this point, because this data point satisfies, or can, if you substitute for 0 and 3.2486 in this equation, it will be equal to 0. Similarly, if you set x2 equals 0, we can get x1 to be 0.3534. So if you set x2 equals 0 here, then 3.2212 times x1 will be equal to 1.1383, and x1 will be equal to 1.1383 divided by 3.2212, that will be 0.3534. So the other coordinate data point is 0.3534, which is x1, comma 0, which is for x2. So try to plot these two data points in this coordinate system and connect them. You'll be able to draw a line that goes to these two data points, and that's your line W times x equals 0. And once you get that, you can just draw parallel lines. That we already have parallel lines, Wx equals 1, Wx equals -1. Okay, so that's the idea we are going to look at in the math. So I just introduced it right away. And in terms of terminologies, so far I called these lines, or these as lines that connect the support vectors in each class. More formally, they should be called as hyperplanes. And that's the terminology we'll actually use if the number of dimensions is greater than 2. Okay. So if you have 3 or 4 dimensions features, that's what it is, then we have to use the word hyperplane as the one that connects the support vectors in each class. Again, you could have a multi-dimensional data set with more than 2 features and run through support vector machine, as long as we have only 2 classes as part of the data set. Now, again, later we will look at how to use support vector machines for multi-class classification as well. But as it is, like logistic regression, support vector machines are primarily designed for binary classification, just two classes. We can tweak it, or tweak means kind of play with it in such a way that it can be used for multi-class classification. But as it is designed only for binary classification. Okay, same thing like with logistic regression. So the hyperplanes, like here we say in two-dimension system, the two parallel lines basically form the decision boundary. So more generally, we say the hyperplanes form the decision boundary. And Wx equal to 0 is also a hyperplane, like a line here that is dividing the decision boundary. So in general, the Wx equal to 0 is like a hyperplane that will divide the maximum margin decision boundary. Okay. Now, so the equation for the dividing line is Wx equal to 0, and the two lines that connect the support vectors in the two classes, the Wx equals 1 and Wx equals -1. The next thing that we will be interested is what is the actual margin, of the decision boundary that separates the two classes. So it really depends on these values of the parameters theta 1, theta 2 in the weight vector. So in general, if you have n dimensions to be the data set, then you're going to have parameters like theta 1, theta 2, theta 3 up to theta n, and then followed by b. So that will be the weight vector if you have an n dimension data set. So if you have 3 dimensions, for example, or 3 features, then you're going to find parameters theta 1, theta 2, theta 3, and then the bias b. So in general, if you have n dimensions, then you're going to find theta 1, theta 2 up to theta n, and then the bias b. The margin of the decision boundary is going to be given basically by this formula. It is 2 divided by square root of theta 1 square plus theta 2 square up to theta n square. So you see that the bias b doesn't really get into this margin equation. So it's only the values of the parameters that get inside this equation. So that this equation basically gives you the margin or the width of the maximum margin decision boundary. So for example, if for this data set, normalized data set we have here, this is the weight vector that we come up with. Then using theta 1, theta 2, we can find what is that maximum margin decision boundary. So the math will give you 0.6172. And if you kind of visualize this more closely, you can interpret that value here, the normalized scale. So I say 0.6172. And if you see here, so this is a line, the blue line is Wx equal to 0, and then you have Wx equals 1, the red line, and the Wx equals -1, the green line. And this is the normalized x1 axis. And you can see this from starting from where the green line hits the x1 axis, and here where the red line hits the x1 axis. So if you look at the values here, 0.0, 0.5, and 0.1. So the basically this width, or you can even say like this, the width is kind of look at this. So this distance that basically separates the two should be almost close to this one. I wouldn't say it is going to be exactly equal to this, because what we are trying to find is something like this. Okay, so that's the width. So that's the width of the decision boundary, but it should not be much different than what we see as like the distance where the two lines hit the normalized x1 axis. That region of separation should be also close to like 0.6, but not much different. Okay, so we can use that as also a kind of a way to interpret what we are trying to find here as the margin of the decision boundary. Okay. Now, why we need to have that bias term in the weight vector. So if you notice, like for this data set here, we go through the math and we find this weight vector. Of course, I'm not showing you the math yet, but after, let us say, assume that after we go through the math, we get this weight vector. And for this data set over here, in order to satisfy the support vectors you have chosen and the margin of separation between them, the math will force a bias term to be part of the weight vector, okay, such that we can accomplish the maximum margin that we wanted to get. So in order to get the maximum margin that we aim for by choosing the two green data points and this one red data point as the two support vectors, and we need to be able to find the values of the parameters such that the wx equal to 0 will be a dividing line between the of the margin as well as the support vectors that we have chosen. You need to satisfy the equation wx equals -1 and wx equals 1. Then the math will see if a bias needs to be added in order to satisfy all these requirements. And in this case, yes, a bias comes out to be -1.1383. If we don't have a bias, or if we do not want to have a bias, then the dividing line will always try to go through the origin. And the green and red lines will be then parallel still. The only thing that we are not guaranteed of is the maximum width of the margin. So is the margin that you're going to find for the decision boundary, is it going to be of maximum width? Not guaranteed. If we prefer not, if you don't want to have a bias. So that's why when we do the math, we will add this term B in the equations so that we are allowing for the algorithm to accommodate a bias if needed in order to accomplish the maximum margin for the decision boundary that will separate the support vectors across the two classes. So by including a bias, we are allowing the wx equal to 0 line to pass through or to cut the x-axis at some data point instead of the origin. If you don't allow the bias, wx equal to 0 will always go through the origin. If you allow the bias, the wx equal to 0 may still go through the origin if that itself gives you the maximum margin. If by going to the x-axis, by cutting the x-axis somewhere else, if that will give you the maximum margin, it will go through that. So like in this case, for this data set over here, it is possible to accomplish the maximum margin only if you and again, when I say for this given data set, basically for this given support vectors, we are not really looking at the other numbers at all. Okay, so that's something to remember. We are not really looking at other numbers to build the model for this kind of support vectors. So I think it's better to say that. And so for the given data set, for this support vectors, and the direction chosen, if you want to maximize the margin, we need to have a bias as part of the math. And that will be this equation that cuts the normalized x1 axis here rather than going through the origin. Okay. So that's why we have a bias term that would facilitate us to accomplish finding an equation for a maximum margin decision boundary that separates the support vectors from the two classes. Okay. All right. I'll just take a short break and then we'll be back. Okay, so let us continue. Okay, so now we'll start looking at modeling which is a data set using a support vector machine. So let's use the same spam email data set that we saw in the case of logistic regression and see how we come up with a model for this data set. So we have two features there. X1 was probably the number of occurrences of the word buy, I believe. And X2 was the number of spelling mistakes in the email. Yes. So those are the two features. And we have a class 1 here representing spam, and -1 is not spam. So as I said, we'll follow the convention that class 1 is representing the targeted class spam. It doesn't matter. We could do the other way as well. But just to be consistent in all the examples or in the course in general, we'll follow the convention that class 1 will represent the targeted class and class -1 for the other class. So this is the raw data set that we have here. And if we plot the two features x1, x2, this is what we get. And so this is the class -1, which is not spam emails. And this is the class spam emails. We have 5 data points for each class. So basically, we have a kind of a margin that separates the two classes here. And so these are the support vectors that are closer. So these are the green data points that are closer to the red class. And similarly, these are the data points that are closer to the green class. Now, we could choose this one as well to be part of our support vector, provided that the line that connects, because these two, S1, S2, primarily are our data points for support vectors for the green class because they are closer to the red ones. We could choose the other one as well if the line that goes through that connects the two support vectors here is also going through this one. If it's not, we will avoid it. Okay, so like here, if the line that connects these two support vectors doesn't really go through this data point, it's kind of like an outlier. So it's more, we can say it's not very close to the red group here, but it's kind of out of this. Now, one thing that we also want to remember that is for any test data point, we'll find Wx equals the value. What is the value of W times X for the test data point? And if Wx is greater than 0, we'll say it belongs to the class 1. And if Wx is less than 0, we would say it belongs to class -1. Now, since we are aiming for a maximum margin that separates the two classes, more likely for the test cases, for ideal tests, unless we purposefully choose data points that fall within the margin, if you come up with a test case just arbitrarily that belongs to class 1, more likely we will have Wx to be greater than 1 for that test case. Similarly, if you come up with a test case that belongs to class -1, more likely you will have Wx to be less than -1 for the test case. You could have something between -1 and 1. We could have like 0.5, but still it belongs to class 1 if it's above 0. And it belongs to class -1 if it's less than 0. So this data point over here, it's going to have Wx, its value to be just slightly less, greater than -1. So it's going to be like -0.9 or something because it's falling within this margin precision boundary. That's still okay. It will fall in the category of the soft margin support vector machine, but it's not really a margin like I showed the other way, like here. The green data point over here is very much close to the red side. It's not that much here. It's still on the green side. That's okay. Okay, so you could choose more than two support vectors in one class, provided all the support vectors are in the parallel line. So first we have to identify the two primary data points that are closer to the other side and give importance to those two data points. Okay, and the other data points like this that are kind of technically, distance wise not as close as these two would be still considered support vectors if that parallel line goes through those data points. Otherwise, just stay with the two data points that you identify to be closest to the other class. Okay, as long as that creates a wide margin. Okay, remember the different cases that I mentioned here. If you're able to allow some like you see here, these two data points are the closest to the red side, but by choosing them, we are coming up with a very smaller margin for the decision boundary. Rather, by allowing this green data point to be considered as an outlier and be part of that margin, we're able to come up with a margin that is reasonably much wider than this one. Then we'll go for the soft margin support vector machine. But we don't have such case in our spam email dataset. It's more clear, it's very clear that we could go with these two data points as support vectors for the green class and these two as the support vectors for the red class, such that we could connect them with a much wider decision boundary. So you basically choose the support vectors with a raw data set. Okay, so we can choose the support vectors with the raw data set itself and then go to the normalization process. Okay. So the normalization, the math is basically done like this. So first thing we need to do is find the mean and standard deviation of the features. So I'll start with my Excel display now. So this is spam email case. So I should have the data set here. Let's see. So let me just copy this. Okay. So we can highlight the support vectors. So these are my 1, 2 is my S1. So 1, 2, just for reference purposes, we call it S1. And 2, 1 is my S2, which is this point here. 2, 1 is my S2. And then 2, 3 is our S3. It's up to us how we want to label them. You can label them the other way around. These two red data points support vectors as S1, S2, and the other, the two green as S3, S4 is fine. It's up to us. So as long as we keep track of the support vectors, that's good enough. So the first thing we need to do is find the mean and standard deviation for the features across the two classes. So for each feature, so the mean so you can say is equals average. So average is the formula used in Excel for the mean. So you're going to include the cells B2 to B11 for all the 10 records. Let me say 1. And then you can copy this and paste here. So that will give the mean C2 to C11 for all the 10 records for feature X2. Then you can find the standard deviation using STDEV. That's so STDEV B2 to B11. So the same set. And then copy and paste this for X2. So this is a mean and standard deviation. The first thing we need to find before we can normalize it. So then what we'll do is we'll go ahead and standardize or normalize. So we'll interchangeably use the term standardize or normalize. Both are going to be the same in this case. So we can copy the structure if you want of this table. Of course, the x1, x2 values are going to be normalized values. So you can say for x1, the normalization is like whatever the value b2, this is 4 there, minus the mean of x1, which is 1.8 that we find here, 1.8, divided by the standard deviation of x1, which is 1.549193. So that's the way we normalize. Whatever the value in that cell, minus 1.8 divided by 1.4191, which is the mean and standard deviation. Press enter. Copy and paste the formula here, but you have to change the mean and standard deviation. So it has to be, let me do this again. Sorry. So it's going to be C2 in this case, that's a value cell number, minus the mean of X2 is 2.2 divided by the standard deviation is 1.032796 for X2. This is the mean and standard deviation. So do that for the two cells for the first record. Use the mean and standard deviation for X1 and then here use the mean and standard deviation for X2. Now copy and paste this. For all the records, you get the mean and standard deviation, the normalized values for all the records. Again, for x1, use its mean and standard deviation. For x2, use its own mean and standard deviation. And that's what I show here as a formula. The normalized for x1 is the raw x1 data, that particular cell in this value says 4, minus the mean, which is 1.8, divided by a standard deviation of x1, which is 1.5492. Now for normalized value for x2 will be raw x2, that will be the 3 here, minus the mean of x2, which is the 2.2 here, divided by the standard deviation of x2, which is this 1.0328 here. Do that for all the cells, we get the standard normalized data. So once we do that, we are, again, the support vectors will remain the same, but we can visualize the normalized data set in Excel, and this is how it comes out to be. Now, if I draw the parallel line again, this is just in PowerPoint. It looks like the parallel line can go through this green data point as well, but to be just on the safe side, we don't choose it as the support vector because we just need two support vectors. That's good enough. Similarly, this this line seems to go through this other red data point here as well. But just to be on the safe side, we don't include something because we need to have a two parallel lines. That's very important. So if data points don't lie on a parallel line, if data points that we choose as support vectors don't lie on a parallel line, then the map will not go. You will end up with nothing. So make sure you just need two support vectors just from at least one of the two classes, preferably from two classes like in this case, but just even one class, two support vectors, and the other class can have just one support vector. We'll see a lot of examples having such a case later. But in this case, we can have two support vectors from each class that looks like this, and we can connect them using a parallel line. So let's visualize this normalized data set. Here. So we'll go through an XY plot. That's what we get. And this. So basically now we have this normalized coordinate system. And we have these two support vectors. So these 5 data points are the green class, and these 5 here are the red class. So technically, these two are the closest. But if this lies parallel to it, that's fine. But otherwise, we don't need. So similarly, these two are the closest to the green class. So it's sufficient to just have these two support vectors. And you can also check. So once you join with the parallel line here, just copy and paste that line here and try to move it to the other side. Sorry, I should probably use arrow. Hmm, that's not working. Let me see if it's possible in PowerPoint. I think it's possible in PowerPoint. Just for verification. Okay. So let's say I don't have this line, but so I have this line. So just copy and move this line using your arrows to the other side and see if you can connect the red data points using that line. So that means that they are parallel lines. Okay. All right. So let us go back to this. So we're going to, this is just for our visualization. We don't really need anything for now. Okay. Then the actual math is starting now. So we have these support vectors. S1, which is negative 0.5164, and X2 is negative 0.19365. I just use 4 decimals here. And remember, we add a 1 as the last feature value is a dummy term, like to account for the bias. So we'll put that 1 as well in the normalized coordinate system. So this really will form our and I want the 1 to be, if I put the 1 here, we can easily see that. So don't do the mistake. So this 1 is the bias term. So S1, S2, we need to remember later when we do the math, are basically belonging to class -1. That's what I make a note of here. And S3, S4 basically belong to the class 1 here. So that's what I'm making a note of here. Okay. So the equation of the decision boundary separating the two classes is W times X equals 0. And the equation of the decision boundary for class 1, class 1 is W times X equals 1, and class -1 is W times X equals -1. So we need to find a weight vector such that by using these 4 support vectors, we want to satisfy these equations over here. So the weight vector, as I said, is going to be theta1, theta2, and the bias term B for 2 dimensions. But it's going to be the theta1, theta2, and B are going to be found basically by using these 4 support vectors in this example here. So we are going to find or fit a weight vector such that it satisfies these 4 support vectors. Okay. So since we chose 4 support vectors, we are going to assign 4 coefficients, 1 for each support vector, and write the weight vector as weight vector equals A1 times S1 plus A2 times S2 plus A3 times S3 plus A4 times S4. I can show the little bit more detail of the math here, just for making it more easy to understand. Let me see. Again, it's not needed for any exam purpose, just for making it more easy to understand. So this is, again, I said the weight vector is basically going to be theta1, then theta2, B. So you may wonder how these 3 terms or feature parameter values can be found using this kind of combination. But remember, this S1, S2, S3, S4 are simply the support vectors that are these data points here. They're not nothing beyond this. So this S1, S2, S3, each are going to have also three terms, like, like you see, let me copy this. They're also having three terms in each support vector. So this is going to be A1 times this vector that has three terms plus A2, and A1, A2, A3, A4 are going to be like constant, some numbers, real numbers, just some coefficients, not vector, just some coefficients. And S2, so it's A2 times S2, which is going to be this vector, and plus A3 times S3, which is this vector, and A4 times S4, which is this vector. So the weight vector is going to be determined or modeled as a linear combination of this four support vectors in this example, and you're going to add appropriately four coefficients. So the key thing now is to find the A1, A2, A3, and A4. If we can find those A1, A2, A3, A4 that satisfies, and no, once we find A1, A2, A3, A4, we can combine with these in this equation with these support vectors, and then find theta 1, theta 2, and b. We're going to do the math. So the math will show you that we can, once you find A1, A2, A3, A4, we can find theta 1, theta 2, and b. But remember, the A1, A2, A3, A4 values that you find need to satisfy these two equations as well, or these four equations. So what are the four equations? W times X equals 1, where at both support vectors S3 and X4. So when X equals S3, W times X should be equal to 1, and W times X should be equal to 1 at X equals S4, and then W times X equals -1 at X equals S1, and W times X to be it is yes, W times X equals -1 at X equals S2. So the values of A1, A2, A3, A4 need to be found in such a way that these four equations are satisfied for each of these four support vectors. And that's the basis we are going to use to find A1, A2, A3, and A4. So what you're going to do is, so as I mentioned here, we need to find the A1, A2, A3, A4 such that the following four equations are satisfied. W times S1 equals -1. W times S2, that's what I said, W at W times X equals 1 at X equal to X3 also means like telling W times S3 equals 1. This is like W times S4 equals 1. This is like W times S1 equals -1, and this is like W times S2 equals -1. So all these four need to be satisfied. So now what is W? W is this thing, A1, S1 plus A2, S2 plus A3, S3 plus A4, S4. So if you substitute for W here, I'll just do 1. So we have this as W. Just use this now. So we have W at times S1 equals 1. Okay, that's what we have here. So equals -1. Yeah. So W times S1 equals -1, because S1 really corresponds to this support vector S1 that belongs to class -1. So W times S1 should be equal to -1. W times S2 should be also equal to -1, and then W times S3 and S4 should be 1. So if I substitute for W to be this, all I have is this multiplied by S1 equals -1. That's all I have. I replace W by this vector A1 S1 plus A2 up to A4 S4 times S1 equals -1. So now you multiply the S1 inside, what you get is A1 times S1 times S1 plus A2 times S2 times S1 plus A3 times S3 times S1 plus A4 times S4 times S1 equals -1. So basically, each term here is multiplied by S1. Again, A1, A2, A3, A4 are simply coefficients. So what's more important is here, we have what's called a dot product of two support vectors. It's like multiplication. We call it as dot product of two support vectors in each of these terms. Okay, I'll do just one more. So we'll do, say, W times S3 equals 1. So it's basically multiplying this by S3. So we're going to have S3 here, S3 here, S3 here, and S3 here equals 1. Okay. So we'll get 4 such equations. And that's what I'm showing here, 4 such equations for each of the support vectors, x1, s2, s3, and s4. So 4 simultaneous equations that need to be solved using any approach that we know for solving linear equations, and we use Gaussian elimination as an online calculator available for that. So 4 equations, 4 unknown coefficients, A1, A2, A3, A4. So we can easily determine the 4 unknown coefficients. Now, however, we still need to find the dot product of these support vectors. So if you notice, the first equation here associated with S1 is basically the dot product of S1 with each of the other support vectors. The second equation associated with S2, so this is associated with S2, involves the dot products of S2 with each of the support vectors. Same thing with S3 involves the dot product of S3 with each of the other support vectors. And this equation S4 involves the dot product of S4 with each of the other support vectors. So each equation involves the dot product of that particular support vector at which you're evaluating this equation with the other support vectors. So what we will do is we will determine from now on what's called a dot product table of the support vectors. Okay, so we'll basically find the dot product between any 2 support vectors, because you see here we basically involve all this. We have 16 dot product terms, and those are the 16 dot product terms. Any support vector with any support vector, including itself. So you have S1 with S1, S1 with S2, S1 with S3, S1 with S4, and this is capturing the dot product of S1 with each of the other support vectors as well as itself. So how to find dot product? That's something we already have seen in some other course or module, but let me do that again. So let us say, let's just use some simple case as example, and then go through this. Let us say some S1 equals 2, 3, 1, and S2 equals 3, 5, 1 as well. Then S1 times S2 is going to be, just do term-wise multiplication and add them up. So it's going to be 2 times 3 plus 3 times 5 plus 1 times 1, as simple as that. Just multiply term-wise is 2 times 3 and then 3 times 5 and then plus 1 times 1. and the resulting sum is the dot product. So this is 6 plus 15 plus 1, that's going to be 22. So the dot product is going to be a number, a scalar value like this. So let us now do the dot product of, say, S1 and S2. So let us do, so our S1 is this, and S2 is this. So S1, the class doesn't really matter in the math, it's just for our reference purpose. So S1 times S2 in this case is going to be, the first term is going to be negative 0.5164 times 0.1291. So we need to be able to do that in our calculator quickly. I'll show that. This is just first for understanding. Times negative 1.1619. And the last term is a 1. 1 times 1. So don't forget about the 1. So this is a 1 times 1. That's 1. So you can take a calculator, and we need to do that for all the cases. So 0.1291 times 0.5164 with a negative sign. That's going to be, sorry, you have to do the plus. sorry. So you have to do the plus. So this is plus. I was treating as a vector, and I'm sorry. So that's 1 times 1. So term-wise multiplication and add them up, like we did in this example. You have to do the term-wise multiplication and add. So once I took a calculator, I realized I missed. So the first term is going to be this. So let's do like this. So it's 5164. Right away go with the negative sign times 0.1291. That's the math. Then plus, open up a parenthesis, minus 0.1936 times 1.1619 with a minus, and close the parenthesis. So this is what is so far, plus 1 times 1 is this. So S1 times S2 is 1.1582. So you can go 4 decimal precision, that's good enough. So this is 1.1583. That is what S1 times S2 is. 1.1583. We'll do a couple of more dot product examples. So let us do S3 times S4. S3 times S4. So this is S3 and S4. So S3 times S4 is going to be 0.129. You don't have to write all these steps, just for understanding. You don't need to write any steps for the dot product thing, just do the calculator quickly. This is just for understanding. I'm writing all this. That's 1 times 1. So we can just take up a calculator and just use the two vectors and do the multiplication. So 0.1291 times 0.7746, that's one term, plus 0.7746 times 0.1936. Be careful the negative value. So it's a negative sign here. So introduce that here right away, the calculation. Close the parenthesis and then press the or enter for the sum of these two product values plus the 1. So that's going to be 0.9500. That's good enough for S3 times S4, which is this. Now, if you have to do S1 times S1, or basically a dot product of a vector with itself, then just square each term and add them up. So that's going to be In that case, you don't need to focus on the negative sign because the square of that is going to be anyway positive. So 0.5164 square. So you can say press star and then say enter, or just you can type twice, but you don't need it. Just press star and press enter. Sorry, 5164. Press just star and then press enter. That's going to be the square of that number. Plus 0.1936 again. After type 1936, type star. When you press enter now, it's going to square 0.1936 as is add with the previous term value. That's together this plus a 1 times 1. So that's going to be 1.3041. That is S1 times S1. We'll do just one more. Say, for example, you're doing S2 square or S2 times S2. That's what it's called. So it's going to be 0.1291 star enter. That's the square of this. Plus 1.1619 star enter. Because again, there's no need for introducing a minus sign because you're going to use square this. Plus 1, that's going to be 2.3667. We can round it to 4 decimal precision. That's S2 times S2. So that's how we do the dot product. I'll just do one more, the last one, just to make sure you're clear on this. So let us pick S2 and S3. And do the dot product. We're just going to use calculator. It happens that the first term is the same for both. That's just coincidental. 0.129 times 0.1291. You can type together again if you want. Then plus 1.1619 with a negative sign times 0.7746 close the parenthesis plus enter overall. Then plus 1, that's 0.1167. You know, approximate like that. So that's 0.1167 for S2 and S3. All right, so this is the dot product table of the support vectors. So basically now you can see the first equation where your x equals S1, this equation we have, basically boils down to everything in the row for S1 multiplied with A1, A2, A3, A4. So it's going to be like A1 times 1.3041 plus A2 times 1.1583 plus A3 times 0.7833 plus A4 times 0.6375. So that's these 4 terms, and it's equal to -1. That's the equation, and that's the equation we have. So for exam purposes, you can just write down the support vectors and these equations, and you can say what your W is, and you can write this if you want to, but you don't really need this step. Okay, instead, you can just find the dot product table, and the first equation is going to be associated with S1 involving the row values. So A1 times this 1.30 in the same order, plus A2 times 1.153 plus A3, because you see this also is S3, A3 times 0.7833 plus A4 also is S4 times 6.6375. Just remember what this class this support vector is representing. That's why I keep noting those classes here. So S1 is representing class -1. So this is going to be equal to -1. Similarly, S2 is going to be A1 times 1.1583 plus A2 times 2.3667 plus A3 times 0.1167 plus A4 times 1.325 equals -1, because S2 is representing -1 as well. So if you are able to remember that, so you just write just this then. You don't even need the other things anywhere in the anything else in the slide for exam purposes. As long as you can remember what it is, you may just write this. And we need to find A1, A2, A3, A4, and then show the dot product table and write the 4 equations. That's good enough. Similarly, this with S3 is going to be 0.78, A1 times 0.7833 plus A2 times 0.1667 and A3 times this plus A4 times 0.95 equals, this is with S3, and S3 is with class 1. So just say equals 1. And the last one's going to be A1 times this, plus A2 times this, plus A3 times this, plus A4 times this, equals again 1. So these are the 4 simultaneous equations that we need to now solve and find A1, A2, A3, A4. So for this purpose, we'll make use of this online calculator. It uses this Gaussian elimination approach. There are different ways you can solve simultaneous equations, and it uses Gaussian elimination. So let us go to that website. And by default, it opens with 3 equations. So if you can play with the number of equations you want. Here we will need 4 equations. So you pull down the menu and choose 4. And you just need to type those coefficients of A1, A2, A3, A4 and equals -1 or 1. And once you type it, you can find the solution. So let me type them. So I'll go through all this for a couple of examples in detail, and then we will kind of skip all this online calculation steps. I'll just write the equations and then say you can use this calculator to find A1, A2, A3, A4. And go like that, okay? Because it's just typing those equations and finding those values. So make sure you type the values correctly. So it's 1.3041. So here use x1, x2, x3, x4. Those are going to be like our A1, A2, A3, A4. So the first equation plus 1.1583 times A2 plus 0.7833 times A3 plus 0.6375 times A4 equals -1. That's it. And then press the tab, and the control goes to the next equation. Is 1.1583 times x1 plus 2.3661 times A2, so the x2 there, 0.1161 times A3 plus 1.325 times A4, which is also equal to -1. And then this is going to be 0.7833 times A1 plus 0.1167 times A2 plus 1.6167 times A3 plus 0.95 times A4 equals 1. And then this is 0.6375 times A1 plus 1.325 times A2 plus 0.95 times A3 plus 1.6375 times A4. Yeah, 6375 times A4 equals 1. So once you type all the equations, we can check whether you have entered all the things correctly, because if you make any mistake here, everything else will change later. Okay, and then click solve the system. It's going to go, they'll show you the math and everything that they went through. We don't need them, but just if you're curious enough. So these are the coefficient values. The one strange thing I notice is they don't really give you the final answer in decimal like this. They show us in fractions. I don't know for what purpose they do that, but you can use a calculator to get the decimal value. So A1, which is x1 here, is going to be negative. Remember the negative sign that is showing up. So make sure you remember that. You notice that negative sign in this case for A1. So it's 3125 divided by 2604. So A1 is going to be that negative value on negative 1.2. And that's what I'm showing here for A1. Similarly, A2 is going to be this. If the numbers are very long, they're going to be very long in some cases. You just copy, just to avoid mistake. Copy the value in calculator and then press Control V divided by this. Copy this. Sorry. Make sure you copy just that number. Control C and divide by and press Control V to copy that value. You're going to get that. So it's point again. This is a negative sign, so it's negative 0.533. For A3. Just copy that. So it's the same thing actually. So it is positive 0.533. Now for A4, if you want, you can copy this just to show you how to do that. So just copy this So whatever be the case, whatever be the number here, just press Control V, that's going to get overwritten, and you just have that number copied there. Press the divide sign, and then 6944, Control C, copy it, and divide it, Control V, and we'll get the answer. It's 1.2. So A4 is 1.2. So it just happens that they are kind of a mirror image in this case because of the pure symmetry in the data set that we are doing. You see here, there's a kind of mirror reflection kind of thing here. It need not be the case with all the examples. Actually, I think this is the only example where we have such symmetry. So don't expect A1, A2, and A3, A4 just to be of opposite sign in the other cases. So once we find A1, A2, A3, A4, we are not done yet. That's kind of first step. So we need to find, remember, the weight vector, which is theta 1, theta 2b. So we just found A1, A2, A3, A4, and we need to now substitute for those coefficient values now, and then substitute the support vector values correspondingly, and go through some small math, and that will give you theta 1, theta 2b. And that's what we're going to do that now. So this is A1 times its support vector S1, not its associated support vector S1, you can say, plus A2. Again, remember there's a plus sign, but since A2 carries a negative sign with it, we'll just say minus. And I don't show the plus here. If I want, I can show the plus, but it's just we're going to add them up. Okay, so we can write the plus here. I should have, but it's just we're going to add them up term-wise. So the 0.533 for A3 times its S3, and then A4, which is 1.2 times S4. So what you're going to do this is, you're going to multiply each term inside the vector with this coefficient, but just add the corresponding terms. So what I mean is, so that's going to find each of these three terms. For theta 1, we're going to add just these first four terms multiplied with the corresponding coefficient values. So it's going to be negative 1.2. Again, you know the sign of the numbers here. So this is going to be negative times negative. That's going to be positive. So don't need to worry about the sign in this case. So 1.2 divided times 0.5164. You can just take 4 decimals if you want, or you can type the entire thing. Let me type the entire thing. It doesn't matter. Once you go up to 4 decimals, it should be reasonably a good approximation. Minus, so now in this case, you see it's a minus times a positive. So overall, it's going to be minus. So that's why if you put a plus here, that doesn't really matter. You're just adding the terms correspondingly. So it's going to be a minus 0.533 times 0.129099473. You get a 0.1291. That's good enough. Now, then this is a plus and plus. So we're going to just say plus 0.533 times 0.129099473. And this is plus times plus. So plus 1.2 times 0.774596838. So that's 1.54919 something. So I just say 1.549. I could have written 2. That's okay. So 1.549, that's my theta 1. So do the same term-wise multiplication and addition for theta 2. So that's going to be this negative 1.2 times the negative value here. So that's going to be a positive overall. Negative times negative is positive. So it's 1.2 times 0.19364. Let's write 5. Or we'll go with 1937 versus 36. 0.1936. Then negative times negative, so it's going to be positive, plus 0.533 times 1.16, you can say 1989 can be written as 919. Here I'm just using 4 decimal places for each term. Then plus This is a plus and plus, so it's going to be 0.533 times 0.77459, so 46. And then this is a plus with a minus, so it's a minus 1.2 times 0.1936. And that should give you 1.0321 for theta 2. And then let's do for B. It's negative 1.2 minus 0.533 plus 0.533, because it's just negative 1.2 times 1 plus negative 0.533 times 1 plus 0.533 times 1 plus 1.2 times 1. So it's all, as I said, they are the same, just the opposite sign, they'll add up to 0. And that's why your bias comes out to be 0 for this data set. So the bias need not be always 0. Typically, you will get something other than 0, but since the data set is kind of more like a mirror image for the green and red data points, we get bias to be 0. That means the decision boundary will go through the origin, because that's just theta 1 and theta 2 terms. And that's what we're going to find now. The equation of the decision boundary that will divide the margin is going to be Wx equals 0. W times x equals 0. So this is our theta 1, theta 2b times x, which is in general x1, x2, and x. Still, you are in the normalized coordinate system. So we'll have a normalized x1, normalized x2 times 1. So not 1, and the third term is a 1 for any data point. So it's 1.549 times x1 plus 1.0321 times x2 plus b times 1, which is b. So it's 0 times 1, which is 0. This is our b here. So this is the equation of this dividing line for the margin. 1.549 x1 times plus 1.0321 times x2 equals 0. So now what we need to do is, we have the normalized coordinate system here. We need to plot that line, see where that line is, get that line here. So we have the two support vectors on each class, and we already have a line that joins them. So now we need to find similarly how to find two data points that find a line that joins them. That will be our Wx equals 0. So this is where we are now. So what we now need to do is, using our approach that I mentioned earlier, just put one feature value equals 0, that will get you the other one, because you have only two features, two dimensions that you're working with. Now, typically we put them to be 0 for the other, actually the other problems here. We could do that. If you put x1 equals 0, you'll get x2 equals 0 as well, because the right side we have 0 and there's no bias. So that basically means it goes through the origin. And that's not sufficient for us. Actually, that's actually sufficient. But to do the rest of the math, we need the two other data points. But we know that it goes to the origin, right? So what we'll do is, we'll draw something that's parallel and go through the origin as well. That's good enough to get Wx equals 0 in PowerPoint as well, something that goes to the origin. But we'll go ahead and determine two other data points that are more meaningful than just being the origin. And I'll tell you the reason for that quickly. And we'll do the same approach for the other, but remember, for the other cases, if there's the bias term, is good to, we can just put x1 equals 0 and solve for x2. Similarly, then x2 equals 0 and solve for x1. But in this case, it won't work because there's no bias term here. So that's why, so if there's no bias term, we have something like this. Instead of x1 equals 0, we'll put x1 equals 1 and see what is x2. We go for 1, we could go for anything else as well, but 1 is something more conventional because this is a normalized coordinate. You cannot just pick something arbitrarily. So we'll just, for x1 equals 1. So if x1 equals 1, This becomes 1.549 times 1, which is 1.549, and it goes to the opposite side. So it becomes 1.549 with a negative divided by 1.0321 because quotient of x2. So x2 is like negative 1 point, so x2 is negative 1.5. So now if you put similarly x2 equals 1, this is 1.0321. And if it goes to the opposite side, it becomes negative 1.0321 divided by 1.549, which is coefficient of x1. So x1 equals negative 0.6663. So the two data points are 1 comma 1 for x1, negative 1.5 for x2. And the other data point is not, don't say data point. Let me see what it is. We just say point because it's not part of a data set. So the other is negative 0.6663 comma 1 because it is x1 comma x2. So plot these 2 points in your coordinate system. We'll do that here. So these 10 records or these data points here will just include these 2 dummy points. So x1 is 1, the other is negative 1.5, and this is 0.6663 for x1 and 1 for x2. So what you can do is, you see right now, all these 10 data points, if you click on this figure here, the chart here, all these 10 data points that are used as a basis to come up with this chart are highlighted in the blue. Just pull down that blue bar to include these 2 points as well, and that will introduce these 2 points. Okay, let me go back. So just click. So this is where we are. So just highlight. If you click on the figure itself, this data set will be highlighted. Just pull down here. You notice now these 2 data points will appear. So this one is our 1 comma point negative 0.6663 comma 1, the second one, and this is our 1 comma negative 1.5. So you can just draw a line that connects these 2 points, and it will go to the origin in this case because that's the nature of the equation. So this is the equation, w times x equals 0, where w is basically the weight vector given by 1.549 and 1.0321 and 0 as the bias. Okay, and you can cross-check. It will satisfy these 4 equations as well that we use as a basis to actually come up with the values for A1, A2, A3, A4. And then we can find what is the margin of this decision boundary. Okay, so remember the margin I said previously is 2 divided by square root of theta 1 square plus theta 2 square up to theta n square. Here we have only 2 parameters, theta 1, theta 2, which are 1.549 and 1.0321. So square them up, add them up, take a square root. It's going to be 1.074. And as I said before, you can go back to the normalized coordinate system and see if the distance between the 2 support vectors is close enough to that. It's just for our visual verification. So 1.074, so something close to 1.1. So we have here, this is negative 1 and negative 0.5, so roughly cutting on the half, so negative, say, 0.7 more on this side. And this is 0.5 to 1, so again cutting more close to 0.5, so close to 0.7. So negative 0.7 to 0.7, that is approximately 1. So that's the margin of this decision boundary, and that's what we get here in the math. Okay. So that's the next thing that we can find, the margin of the decision boundary. And we can do a lot more, actually. I'm showing the slide. Okay. We'll take a small break and come back. All right. Okay. So the next thing we could do is actually like we did the theta x and the logistic regression for each of the data points, we could find what is the w times x value here and see whether they are getting appropriately classified. So that's what I'm going to do that. So we have the theta values. So once we join the and once we get wx equal to 0, we don't really need these 2 points. We can just go back to the previous thing. All right, so let us now find w times x. All right, so our w is 1.49. So this is the equation w times x. So that's going to be 1.549 times x1, which is in this case h2, sorry, times h2. This is this plus 1.0321 times x2, which is our I2, and enter, because wx will be equal to 0 just for this line. The data points are lying somewhere else. So we just need to find what is the value of w times x. If the w times x comes out to be greater than 0, it belongs to the red class, which is class 1. And if it's less than 0, it belongs to the class -1. And let us see what it came out to be. It came out to be 2.999 something, so it's greater than 0, and it's class 1. And it should be actually expected to be greater than 1 as well, because the first data point actually corresponds to, let me check, where is it? Should be far away from the decision boundary. Same thing that we saw in logistic regression. If the data point is far away from the decision boundary, its theta x value there was higher. Similarly, here's wx value will be higher. So this was actually the first data point, which we just evaluated. So this is our 1.42 and 0.774. And this, you see, this is far away from wx. So this is our wx equals 1. This counting these 2 support vectors. So it's much farther from it. So it's expected to be much greater than 1. And that's what we have it here. So copy and paste that formula here, because we just need the cell numbers for the other data points. So if you do that here, you get for the second data point, which is actually a support vector x1, and it comes to be negative. It's almost -1 here. And that's what it is. W times S1 is expected to be -1. And this is our, I think, S1, the support vector. And we can actually do it for the other data points as well. So this is -2, much less than -1. It is 1.161, so it's somewhere on this side, like this one. So it's far away from this negative. So the -1 class line is going to be this one. So it's much farther away. This data point is far away from this -1 line. So it's reasonably expected to be -2. Then this is our decision boundary at S2 is -1. So we get -1. So you can cross-verify whether your math is correct and also see if all the other data points are getting appropriately classified. So this is expected to be in class 1. And you see, this is our data point here that we didn't consider. So this is 1.42 and -1.16. So the wx value for this comes out to be almost 1. So this could have been included as a support vector, because that means the line that joins this like this would have been a parallel line to this as well. Okay. That's what I said. Once you have 2 support vectors, preferably from each class, but at least one support, once you have at least 2 support vectors from one of the 2 classes, you're good enough. In the other class, you just need 1 support vector. Okay. So 2 and 1 is what at minimum we need. 2 support vectors from one class and 1 support vector from the other class is just the minimum you need. Anything beyond that won't add much information. Okay. If you could go for 2 and 2 like we did in this example, that's good. That's fine as well. But you could have just gone with 1 if you want to simplify the math. Remember, we went through the math, and we remember the number of support vectors we choose decides the complexity of the equations. Since we chose four support vectors, we had four simultaneous equations to solve, and we have a dot product table involving four support vectors. If you choose three support vectors, then you're going to have a dot product table involving only three support vectors, and then three simultaneous equations we need to solve and find A1, A2, and A3, and go on. The other examples will illustrate that. So as a practice, if you want, just choose S1, S2 from the green class, and S3 or S4 from the red class, and do the math. Or S3 and S4 from the red class, and just S1 or S2 from the green class, and do the math. You should get the same equations. Okay, if you want, you can do as practice. So let us finish this verification thing. So can copy and paste. So we get -1. Similarly, this data point could have been chosen as well. It looks like to be kind of making a parallel line. This is 1, close to 1, and this is -3, -2, and this is support vector should be 1. So that's the kind of WX evaluation for the entire normalized data set. Okay, so that's the next thing I wanted to show. So now you could go through some testing. So far we tested only the actual data set that we are given with. But remember that itself is a testing, because we didn't choose, like unlike logistic regression, we didn't choose the entire data set for our modeling. We just used these four data points, the support vectors. So computing WX for the other data points itself is a testing, because we didn't use them for modeling, and trying to see if the WX value comes out to be greater than 1 or less than -1 or even greater than 0, first to be simple, itself is like a testing. Greater than 0 or less than 0 is the testing. Beyond that, we could test for any other test case that is not part of the data set. So I'm showing here a couple of such testing cases. So let's say x1 equals 1 and x2 equals 5. Again, this is now the raw data set. Raw value of x1 is 1 and raw value of x2 is 5. So that's what is given to us, because for example, this could be like, I get an email, it has one occurrence of the word by and 5 spelling mistakes. That's what it is. X1 equals 1, x2 equals 5. And now we need to evaluate do a prediction whether that email could be a spam email or not. That's kind of the testing we are doing now. So since we have the case so far in the normalized coordinate system, we need to convert the test data point to a normalized data point, and then go through the testing process. Because remember, all these things that we had here are normalized values of the actual data points. Let me save this. Okay. So this is a spam email case. So we need to transform this to normalized scale, and we know how to do that. Just use a formula. The value raw data x1 minus the mean of the x1 divided by standard deviation of x1. So again, the raw minus mean inside the parenthesis, the whole thing divided by standard deviation, as I showed here. So for x1, the raw data is 1 minus 1.8. So that's the whole thing inside parenthesis. The whole thing divided by the standard deviation 1.5492. So that gives you negative 0.5164. Then for x2, similarly, it's 5 minus its mean 2.2. The whole thing divided by the standard deviation 1.0328. That comes to be 2.7111. So negative 0.5164 is a normalized x1, and 2.7111 is the normalized x2, and then our bias 1. So this is our corresponding uh, data point in the normalized coordinate system for this x1 equals 1 and x2 equals 5. So now that's our x here, and we can substitute in this equation for w times x and see what we get. So that's going to be like w is theta 1, theta 2, and b is 0, of course. So this is theta 1 times x1 plus theta 2 times x2 plus b. So 1.549 times this is our normalized x1 plus 1.0321, which is our theta 2 times normalized x2 plus nothing for b because b is 0 in our equation. W times x equals 0. This is what we have, w times x. And in this case, what we get is 1.9982, which is greater than 0. That's the first test we have to do. Is it greater than 0 or less than 0? If it's greater than 0, it belongs to class 1. If it's less than 0, it belongs to class -1. Since it's greater than 0, it belongs to class 1. Now, how far it is from 1, that is our wx equals 1, will tell you how far is the test data point. So if we plot this negative 0.5164 2.711 in the normalized coordinate system, this is where my test data point comes out to be, the yellow one. And you see, this is farther away from this red line, which is the decision boundary for wx equals 1. So if it was close to this, it would have been like 1 point something, but this is like reasonably far away from this. So it makes sense that we get this wx value to be like almost 2. Okay, so let's do one more testing. Let's say our x1 and x2 are both 1. It looks like a not spam email because there's one occurrence of by and one spelling mistake. Whereas here you see one occurrence of by and 5 spelling mistakes. That 5 is the one really that made it to belong to the other class, spam class. Whereas here we fix that x1 equals 1 and just reduce the x2 instead of 5, it is 1. So go to the math as usual and get the normalized version of this. The normalized x1 is going to be the same because we didn't change our x1, we changed our x2 only. So x2 will be like the 1 minus the normalized value 2.2, the whole thing divided by 1.0328. So that's coming out to be negative 1.1619. And then we have a 1. So do the dot product, 1.w times x, which is theta 1 times x1 plus theta 2 times x2. So this is coming out to be negative 2 almost. So it's less than 0, first of all. So it belongs to class -1. And it's much farther away from the line -1, wx equals -1, because you see here, this data point really is somewhere much below that decision boundary. So that's a not spam class. Wx equals -1 belongs to class -1. Okay. So that's the next thing we could do. So now what we could also do is we could transform the results back. So we got all the results so far in the normalized coordinate system. We could just transform everything back to actual coordinate system. So we could test like this and be done with everything. So that's the end of probably an example explanation of support vector machine. But just for additional information, I'm also showing that we could kind of move all the results that we got in the normalized coordinate system back to the actual coordinate system and visualize things there. Okay, and that's what I'm going to show in the remainder of this example. So to do that, what we'll do is take the wx equals 0 equation, and we already did this. We found the 2 points that go through this line, the 2 reasonable points other than the origin, which came out to be 1, negative 1.5, and this one. Similar to what we did for the testing, but it's the other way now. We have the normalized value. So this is one normalized x1, x2, and we have the mean and standard deviation for x1 and x2. So to get the, let me copy this formula here. It is normal. Okay. So to get the normalized value from the raw data, you do this. Raw value minus the mean of x1, the whole thing divided by standard deviation of x1 to get the normalized x1. So now we have normalized x1, we have the mean of x1, we have the standard deviation of x1. We need to find the raw x1 equivalent for, so for example, if we take this data point, the normalized x1 is 1. So what is the corresponding raw x1? That's what we're trying to find out. So for x1 equals 1, the raw, which is actual coordinate x1, is going to be the normalized x1 times, if you do the math, this is like the standard deviation goes to the other side, cross multiplication. So normalized x1 times the standard deviation, then this negative mean on this side goes to the other side, becomes plus mean. And that's the main formula we have here. So the raw x1 is going to be the normalized x1 times the standard deviation of x1 plus the mean of x1. That's the conversion between the two. Okay, so let me, I think that will be clear, but I can add a couple of things here. Doesn't get crowded. So the raw x1 is a different color, is going to be the normalized x1 times the standard deviation of x1, the whole thing plus the mean of x1. Okay, so same thing for raw x2 as well. So the raw x2 is going to be the normalized x2 times standard deviation of x2 plus the mean of x2. So once we do that, so it's going to be 1 for this is with x1. So 1 times standard deviation of x1 is 1.5492 plus the mean of x1 is 1.8. So 3.3492 is the raw or actual x1 value. So we can say actual or raw. Okay. I used actual, but it's the same as raw. So I think that's for rest of the slide, I use actual. So let's stay with that. But just I'm here typing actual is same as raw. And it comes down. And this is actual raw. Okay. So similarly, for this negative 1.5, still we are in this first point. That's x2 though. So that's going to be the standard negative 1.5 times the standard deviation of x2 plus mean of x2. So this is the math for that. So for negative, 1 comma negative 1.5 in the normalized coordinate system is same as 3.3492 comma 0.6508 in the raw or actual data set or system. Similarly, this negative 0.663, which is normalized x1, its actual x1 is going to be this, which is obtained by multiplying the normalized value times the standard deviation of x1 plus the mean of x1. So mean of x1 should have been here. That's why it went over there. So we get 0.7678. Similarly, the actual x2 for this normalized x2 of 1 is going to be 1 times standard deviation of x2 plus mean of x2. And that's what I have here. and that's coming out to be this. So negative 0.663 comma 1 is same as 0.7678 comma 3.2328. So why we went through this process? Because we have the raw data set. To go back to this, we have this raw data set. We didn't do anything so far the raw data set. We just went through the normalization process and did everything in the normalized system. But let us just plot the raw data set as it is. This is what we have. Okay. And so now what we could do is similar to what we did to get the equation for to visualize Wx equals 0, the normalized scale. But remember, Wx equal to is not 0 for the normalized. Sorry, it is equal to 0. Second. Let's first put the. So the coordinates that we got are 3.3492 and 0.6508. That's one raw x1, x2. Okay. So I'm going to type that here for. So for that, one of the normalized points, we corresponding raw data is 3.3492. What is that? Doesn't matter which one it is. It's the first one, which is 1 comma negative 1.5. So 3.3492 x1. Make sure you type it right. So this is our corresponding x2. The other one is 0.7678 for x1 and 3.2328 for x2. So that visualization that we have here so far includes only the first 10. You click on this, only the first 10 are highlighted with the blue. So now if you drag down this blue region to these 2 points, these two will show up. So this is your 0.7678 comma 3.2328, and this is your 3.3492 and 0.6508. Like we did before, we can join these 2 points as well, and that's our decision boundary. Now, the W vector that we found so far and used in our calculations, which was our just this W vector that we have is only for the normalized coordinate system. It cannot be just so we cannot say the equation for this is that 1.549 times x1 plus 1.0321 times x2, because that's for the normalized system. Okay, so we cannot say we cannot come up with an equation for this using these two. We cannot come up with an equation using the theta1, theta2 that we had found, because that's only applicable for normalized coordinate system. So we will, instead of calling it as W times X, we will call this as some W prime times X. Okay. Now we can say it's W prime times X equal to 0 and call it as the dividing decision boundary for the actual coordinate system. But what is that W prime? We don't know that yet. Okay. But we got a clue. We got these 2 points, that go through this line, because we're basically joining these 2 points to get the decision boundary. So if we use the idea from analytical geometry fundamentals in math, if you have 2 data points, x1, x2, and say not x1, x2, x1, yeah, let's use this. the standard formulas is if you have 2 points x1, y1 and x2, y2 in an xy coordinate system, and you want to have an equation for a line that connects these 2 points, the formula is y minus y1 divided by y2 minus y1 will be equal to x minus x1 divided by x2 minus x1. So this is the equation of a line that connects 2 points. So for example, if the 2 points we are looking at are say 2 comma 3, or even let's pick up this one. Don't need to go for some other points. 3.3492 comma 0.3 our x1 x2 as x and y. Okay, 2 coordinate systems. So this is one, and so I'm treating the x and y as x comma y is x1 x2, so you can use that. And the other point is 0.7678 comma 3.2328. So these are 2 points. So now you want to plug it in this equation. So you can just use this for reference. This is our x1, y1. And so this is x1, y1. And this is your x2, y2, the 2 points. Again, I'm using xy as a coordinate system here instead of x1 comma x2 because that might be confusing. So this is a standard analytical geometry formula. So if you replace the variables, so y1 is here 0.6508 and y2 is here 3.2328 minus 0.6508. So I have to kind of extend all these things. Minus x1 is 3.3492 divided by x2 is 0.7678 minus 3.3492. So if you simplify the math beyond involved in this, we get the equation. All right, so let's simplify this here. So 3.2328 minus 0.6508 is 2.582. So this is 2.582. And what is this? 0.7678 minus 3.3492 is also 2.58 something. So negative 2.5814. Now, the difference, because here you get 2.582 and negative 2.584, they're basically both the same numbers. This is the sign difference. This difference is minor difference is due to the rounding that we did in all the calculations. So we can kind of consider this as the same. Just in this example, it happens sort of the same. Otherwise, you have to go through the math behind this as well. We'll do that for the next example. So for this example, since both the denominators, this case happens to be the same magnitude, just the sign difference, you can say this is 1 and this is -1. And just multiply on both sides. So we can say this is, or just deal with that side. So y minus 0.0568 is, this is x divided by -1, so that's minus x. Negative 3.3492 divided by -1, that becomes plus 3.3492. And just simplify this, bring the x to the side and everything to the side. So basically x plus y minus 0.6508 minus 3.3492 equals 0. And if you add these two, This is actually going to be 4 in this case. 3.3492 plus 6.0 is both minus, so they are up to 4. 4 equals 0. So this is the equation for the decision boundary W prime times X equals 0. Again, the X here is the raw data. Okay, so now we need to replace XY with X1, X2. So that's going to be like W prime times X equals 0, same as X1 plus X2 minus 4 equals 0. So X is replaced with X1 and Y with X2. So this is the equation for our decision boundary in the raw coordinate system. Okay, so the equation for this is in the raw coordinate system is X1 plus X2 minus 4 equals 0. So we can now what do is go through one more step. So that's our W prime times X. So X1 plus X2 minus 4. That's the equation. So there's no, so both the coefficients are 1 here. Okay, but we're not interested in doing anything with the coefficients. We just want the decision boundary, which we got W times X equals W prime times X equals 0, which is X plus X1 plus X2 minus 4 equals 0. And let's plug in the numbers. So X1 is B2 here for this data point, just testing now, C2 minus 4. So X1 plus X2 minus 4 and see what it is. It's 3 greater than 0, so belongs to class 1. So anything above 0, because the same thing that we got here, anything greater than 0 belongs to class 1. Anything less than 0 belongs to class -1. Same convention. So copy and paste the values. And the support vectors, we get same values. So because they belong to it's -1. And then this is -1 as well, and this is 1 and 1. So the other cases, those data points are away from the decision boundaries. So we get something less than -1 or greater than 1. Okay, so basically, if W prime times X is greater than 0, it belongs to class 1. If it's less than 0, it belongs to class -1. And this is something we can do now for testing as well. So if we got our 1, 1 that we got before, so 1 plus 1 minus 4 is -2. 1 plus 1 minus 4 is -2. So it belongs to class -1. Whereas 1 plus 5 minus 4, we got X1 as 1, X2 as 5. So 1 plus 5 minus 4 is 2. So it belongs to class 1, positive, greater than 0. The same testing we did before can be done with the actual raw coordinate system as well. So only thing is, we are not applying this decision boundary directly. Okay, so we are going through the normalized coordinate system approach and then transforming all those, basically the 2 points. So the critical thing is, we are trying to find 2 points in the normalized coordinate system through which the W times X in the normalized coordinate system goes through. And then using those 2 points to transform to the raw coordinate system and getting those 2 points in the raw coordinate system and coming up with a straight line that connects the 2 points. And the equation of that straight line that connects those 2 points is the equation of the decision boundary in the raw coordinate system. And that's the W prime times X equals 0. And so for any X, if W prime times X is greater than 0, we get, we call it belongs to class 1. And if it is less than 0, it belongs to class -1. Okay. And that's the testing we can do for all the points. Again, remember, we didn't, of course, we use the support vectors in the normalized form. That's why we get -1, -1 for the negative class 1, -1 support vectors, and 1 for the class 1 support, because we just used a normalized version of these data points to actually come up with the model. So that's why when you transform to W prime times X, we also get 1, 1, negative 1, negative 1 for the support vectors. But for the others, we get something greater than 1 or something less than negative 1. Okay. So we'll take a break with this, and then we'll go through the other examples.